for the Nelson A. Rockefeller Institute of Government, co-organizers of today's program, Facing the Storm, Severe Weather Challenges Confronting New York State in the 21st Century. On behalf of our director, Tom Gaze, and our partners in this event, the University at Albany's Department of Atmospheric and Environmental Sciences, the National Oceanic and Atmospheric Administration, and the following SUNY campuses, Stony Brook University, and also I should mention, also coming in, Nassau County Office of Emergency Management, SUNY New Paltz, SUNY Plattsburgh, SUNY Potsdam, the SUNY College of Environmental Sciences and Forestry, and SUNY Oswego. We are indeed delighted to welcome you to this important event that will be considering a problem that will likely affect each of our agencies and organizations here present, as well as tens of thousands, if not more, of the state's citizens. That problem is increasingly severe weather throughout New York State. I would also like to take this time to recognize the support of our global technology provider, Cisco, a corporation that has provided unlimited commitment to this event, which has allowed us to bring our SUNY colleagues from throughout the state together as one. I should mention that right now, as we sit here, we are joined by approximately 500 of New York's representatives at our 7, actually 8 locations statewide, and that has not been without a little bit of work. It is our hope that through the information you gain today, we will all be prepared for what occurs in the years ahead. Could I ask for a round of applause for our partners, please? We have a very full agenda, so let me limit myself to a few brief administrative remarks before we begin. The 7 campuses are only scheduled to be all together for the first half of our program. After the third presentation in panel 1, we will move into our statewide question and answer period. The remote campuses will be muted throughout our initial presentations. We won't be able to hear them. If there is a question from the field when we move into the statewide Q&A, we're going to ask that the site moderators at each of the states raise their WebEx electronic hand and that you wait for us to call on your site before the questioner begins so that we can unmute you and we can mute Albany. Please ensure, and this is for the remote sites, that the questioner is in a position where he or she can be easily heard. That will include here in Albany, where we will ask for questioners to queue at the microphone in the middle of the room, you see it there, and wait to be called upon. After the conclusion of the question and answer period, we will conclude our Albany joint program, and all locations will move into separate programming that's focused on their local issues. Should your site need to drop off prior to that time, approximately 10:45, just sign off and move into your local meeting, and again, that is for the remote sites. I'm not going to ask a room full of emergency managers and government officials to turn off their electronic devices, but if you can please put them on vibrate, we would greatly appreciate it. It's now my pleasure to introduce for a very special welcome the President of the University at Albany, Dr. Robert Jones. Robert?
Thank you very much. It's indeed an honor and a pleasure to be here this morning, and it's a pleasure for me to welcome all of you here on behalf of the University at Albany for this very, very timely and very important conference, Facing the Storm, Severe Weather Challenges Confronting New York State in the 21st Century. First of all, I'd like to thank Tom and Bob for all the outstanding work that they've done for the second year in a row to pull this conference together and to leverage technology and to use innovation to bring multiple campuses and participants to this forum. I'd also like to thank the Department of Atmospheric and Environmental Sciences, the National Oceanic and Atmospheric Administration, the New York State Emergency Management Association for developing this event as well. This is the second year, as I said, that Rockefeller Institute of Government has been co-hosting this event with the University at Albany, and we certainly hope that this tradition will continue in the years ahead. This forum is designed to bring together a broad range of expertise needed to address severe weather. These climate events greatly tax the energies, resources of government, agency workers, and a host of nonprofit human services providers. I think we all would agree that we need better information to To be prepared, we need to be able to respond more effectively, and we recognize that the entire state will benefit significantly from all of these efforts. The University of Albany itself is very proud to play a part in mitigating the harsh results of extreme weather through involvement with the developing MesoNet, which, as most of you know, is 125 weather stations that will be networked across the state of New York. Once implemented, this system will provide weather predicting models and decision-making tools that will be in effect in every county in the state. Albany was also chosen for this role in part because of the Department of Atmospheric and Environmental Sciences and our Atmospheric Science Research Centers possesses the largest concentration of climate scientists in the state and is one of the most well-regarded academic departments in the nation. Our weather researchers, along with the university's cybersecurity, homeland security experts, were also very integral in the governor's decision to name the University of Albany as the site for the nation's first integrated College of Emergency Preparedness, Homeland Security, and Cybersecurity. This new college will work to prepare the next wave of professionals to prepare for, protect against, and respond to, and recover from a growing array of risks and threats, including the increased incidence of severe weather. The new college will convene a diverse group of experts from the University of Albany, but as well as other universities and agencies across the state. The goal is to provide high-quality academic program for undergraduates and graduate students, to produce new knowledge by way of innovative research, and to deliver training and lifelong learning opportunities for professionals. Through this integration with the public and private and nonprofit sectors, the college will be able to collaborate closely with a wide array of professionals working in the field. These partnerships will allow us the opportunity to blend interdisciplinary academic learning with the opportunities for real-world experience through training, internship, and applied research. For all of these reasons and for many more, we are very glad that you are here with us today, and I thank you all for being here, and we wish you a most productive and enjoyable morning. Thank you very much.
Congressman Paul Tonko was here last year with us, but was not able to be here today because of business that keeps him in Washington, but as is appropriate, is joining us virtually from DC. And so, without further ado, Congressman Paul Tonko.
Severe. how we might use forecasting tools and explore best practices to foster greater cooperation between government and emergency management communities is so valuable as we look to advance our disaster response and mitigation efforts. But programs like these are not enough if they are only offered once. And that's why I am so glad to know you have all gathered again, this time in greater numbers and more locations statewide. One of the most critical programs to come out of last year's meeting was the commitment by the University at Albany and its Department of Atmospheric and Environmental Sciences, the Rockefeller Institute, the National Oceanic and Atmospheric Administration, and the New York State Emergency Management Association to continue this annual event for local and state officials, the media, the public at large, as well as emergency management, academic, and nonprofit communities. As a former New York State Assembly member for nearly 25 years, and now as a member of Congress who represents communities impacted by disaster and floods, I take very seriously my responsibility to advance the use of data and technology that will better equip us to mitigate the high toll of severe weather, to make the case that it is well past time to combat the negative effects climate change has on our planet, and to step up our efforts on a national level to provide assistance and coordination to local communities and first responders for the next storm of the century. New Yorkers have a resilient spirit, but we shouldn't have to rely on that resiliency when the problems we are facing today are completely avoidable through a serious and sustained investment in our environment and new technologies. We must start now because an endless cycle of adapting to a changing climate instead of working to prevent that change is not a tradition I want to hand down to the next generation of leaders. We can bury our head in the sand when it comes to climate change, but when severe weather washes that sand away, we'll see that time has passed where we could have done something to prevent it. The longer we let a small but vocal group of these climate deniers dictate our energy policy, the longer we are delaying a solution to our problems. Through programs like the ones you are all here today to develop, it is my hope that we will become better prepared to find those solutions to the problems laid before us. Again, I wish I could be here with you today, but I wish you the best for a productive discussion that springs us through the rest of the year and another symposium such as this in 2016. Thank you.
We're very grateful to Congressman Tonko, and also I wanted to recognize one of our other elected representatives here in the audience with us. Could Senator Carlucci please stand and be recognized? Thank you, Senator. I would now like to ask the presenters for panel one to please join us on the stage. This will take place, and then again a reminder, we'll move into our statewide question and answer panel. I'm going to introduce them in the order of their presentations. First, Christopher Thorncroft, Chair of the University at Albany's Department of Atmospheric and Environmental Sciences. Lance Bozart, Distinguished Professor for the University at Albany's Department of Atmospheric and Environmental Sciences, and David Valley, Hydrologist in Charge for the National Oceanic and Atmospheric Administration's Northeast River Forecast Center. Chris, you'll lead us off.
Good morning. I'll talk about this.
What's that? Just go ahead and start talking.
Okay, so it gives me great pleasure to be back here today with a strong message about climate change and how that's going to be impacting the Northeast. Climate change is a huge issue that we should not be shying away from, and I'm going to be showing you today some information that highlights the global trends in temperature in a very understandable way. and eventually lead down into the small scales down to New York State, because one thing is global. But everyone in New York, of course, wants to know how it will affect New York. And then ultimately, we're discussing how we deal with that. So while we still load this up, I'll highlight the theme for you, and then I'll give it to you. So the theme here is to talk about global climate change as a problem that needs to be dealt with. I will show you how this is affecting New York in terms of its impacts on extreme weather, which is very convincing. And then we're going to talk about weather prediction and the tools that exist as part of a mitigation activity that needs to be dealt with by New York. And I'm going to be stealing a phrase from the National Weather Service, who's telling us to get ready prepare for a weather-ready nation, which means we have to be smart with weather information that we have, both in terms of forecast information, but also in observations. Not only do we need to be weather ready in terms of weather forecasts, we need to be linking those weather forecasts to decision making, ultimately in the aim to save life and property. So knowing a weather forecast as it evolves in time, how do we deal with a forecast that changes with various lead times? So that's a decision that emergency managers need to deal with every day with this extreme weather. Also, linking to later talks, how do we deal with weather forecasts and ultimately probabilistic information? How do we communicate the changing risk of a weather event as it plays out? How do we deal with that communication to the public? A big issue that I want to promote here is the idea that not every forecast can be what we call deterministic. Some forecasts what deterministic means that we can forecast the exact weather in 5 days from now, but we can't do that. So there's always a probabilistic aspect to weather forecasts. And how we communicate that risk, I think, is still a challenge to the public, but also to the people that have to make decisions. So if you have a 50% chance, if we have a 50% chance of a devastating weather event, and you have high exposure, what do you do if that probability drops to 20%? Maybe you don't do anything different because the exposure is so great. So can we start? So this slide, if it's going to start running, shows you that in New York we're actually we're getting used, unfortunately, to extreme weather. 20 disasters have been declared in the state since 2006. Many of these have been associated with rainfall and flooding, and that will be a theme of this talk. And 6 recently been associated with snow and icing. One of the issues that makes New York special, if you like, that we can get extreme weather any time of year, be it snowstorms or ice storms in the winter, or be it flooding events or high rainfall events other times of the year. So are you able to advance the slide? So I am very, very keen to set the stage for this. While we're caring about impacts, it is very important to be aware of a global issue related to global climate change. The next slide actually has an animation on it. If you move the cursor up and click up here. Okay, it's not an animation. What this animation should have told you is over 120 years the planet has warmed substantially. And if you can just go to the next slide, I have a time series that shows it in a slightly more boring way. This represents a global surface temperature time series from 1850 to the present. And clearly you can see at the end of the 18th century, end of the 19th century, beginning of the 20th century, it was much colder than it is now. The world has warmed by about 1.4 degrees Fahrenheit, and which is a significant growth. So the question is why do we have a globally warmer planet? So we go to the next slide. Oh, so first of all, before I do that, just to show you that last year, this is the temperature anomaly for the last year. Globally, the planet was warmest. It's the warmest ever year on record. It's interesting. In the Northeast, we were actually cold last year, and that's reminding us there's a lot of natural variability. Through many parts of the year, there was actually a stationary trough or weather system that affected the global temperature. But globally, you can see the planet is much warmer than it was 100 years ago. And the 10 warmest years in the instrumental record, with the exception of 98, have now occurred since 2000. So next slide. So the question is, why is the planet warming up? So the time series here shows you an increasing trend in carbon dioxide, which is man-made. And I'd like to quote this: 97% of climate experts attribute the global warming signal to the activity of humans, basically the burning of fossil fuels. 97%. And so it's not, for those people that know a lot about the science, 97% of those realize the facts that man is affecting the temperature of the planet. So go to the next slide. And not only that, these are various American scientific societies, academies, and US government agencies, all of which have very strong statements that suggest, that highlighting the role of man in changing the temperature of the planet. I think it's a brave person that stands up and says they don't believe in climate change. If we go to the next one. And the next one is just a quote from the IPCC. Warming of the climate system is unequivocal. These are global experts in climate change. Since the 1950s, many of the observed changes are unprecedented over decades to millennia. The atmosphere and ocean have warmed, the amounts of snow and ice have diminished, sea level has risen, and at the same time, greenhouse gases have increased, largely due to man's behavior on this planet. So as I repeat, I think it's a brave person that goes against this strong view in the scientific community. Next slide. So that's a very global view. It's a big view. It's very important. A lot of politics involved in that. So let's just drill down into the US and the Northeast. We go to the next slide. This slide shows you the US impact in terms of sea level rise. This is New York City. Since 1900, the sea level rise has risen by a foot. That clearly is going to have an impact when we have a storm surge. It's going to be higher, for example. So that's clearly impacting our coastlines. Go to the next slide. The next slide shows a temperature change over the century. So in the Northeast, it's typical. We've had about a 1.4 degree Fahrenheit warming, consistent with the global warming signal. And much of the country is warmer. Go to the next slide. What happens when the atmosphere warms up? It has the capacity to hold more water in it. When there's more water, you can get more rain, and you can get more intense systems. And I highlighted this last time. This shows you the trend since 1958 of the change in the most intense rainfall systems. The top 1%, the ones that really cause the most damage. And so in the Northeast, we've seen a 74% increase in the frequency of those systems, even more than anywhere else on the state. So climate change projections are also telling us that this trend is likely to continue. And it makes sense. The atmosphere is warmer, holds more water. The systems can then tend to be more intense. And that's clearly important for intense rainfall and flooding. Next slide. So this is what I want to get to talk about weather. We need to be weather smart, and I think this is part of our national strategy. We need a weather smart nation. We need a weather smart New York. We've had a lot of intense weather. We need to get ready for more. And there are various bullets here that highlight what we need to be thinking about. We need to exploit the numerical weather prediction forecast provided by the National Weather Service at a range of timescales, extended weeks, days, even down to hours. We need to link those forecasts and the probabilistic forecasts to decision-making. How do you make a decision based on a 50% chance of a strong event versus a 30% chance? These discussions have been ongoing for a long time, and people are dealing with it. I'm going to hear a talk here later about how we deal with that. Forecasts and related risks need to be communicated effectively to the public. This is a really important, actually, social science question. If there's intense rainfall leading to a flood, and you need a reaction from a member of public, how do you communicate the risk appropriately and going forward in time? And then ultimately, a huge challenge, the weather forecasts predict weather variables, but many of these things are impacting things like flooding, mudslides, which is very topical here in Albany, fire, air quality. So there needs to be more communication and actually work to make sure that these probabilistic forecasts are communicated appropriately to the people working on these impacts. So let me just go the next slide onto the numerical weather prediction. I wanted to highlight the various timescales that exist for us to deal with. There are long-range forecasts, 1 to 2 weeks, where our weather could be impacted by something going on in the Atlantic. An Atlantic hurricane could take 2 weeks to get to here. We need to be dealing with those. We'll hear in the next talk about how an anomalous weather system in the Pacific can affect New York. So these are very long range, very definitely dealing with probabilities of outcomes. Then we start getting to the medium range, 3 to 6 days. Forecasts are hopefully starting to converge, hopefully, I say, to converge on a solution. And then we get short range, 12 hours to 2 days. And that's where we need more in situ, high quality data, closer obviously to the region where we're getting impacted. And also feeding into much higher resolution numerical weather prediction models. Now I go to the next slide. I just wanted to highlight also another type of forecasting, which is nowcasting. This is basically looking at the weather now and predicting what's going to happen in the next 12 hours. And that's where you really need the better in situ guidance on what's happening and high quality observations to do that. So where is it snowing? Where is it freezing rain? Where's the line? Where is it fog? So you knowing that now across the state will be very useful for predicting the next 12 hours. So it's a seamless distribution of forecasts going from quite long range down to very short range. And each of these forecasts requires some sort of decision to be made, if it was particularly an emergency manager, but also informing public. Go to the next slide. So one thing that I wanted to emphasize today was the idea that weather is we don't always know exactly what's going to take place. And we're dealing with probabilities. So certainly when you're talking about a two-week forecast, there may be several possible outcomes that are equally valid. So that's like rolling a dice, so it'll be 1 to 6. Each of those sides is equally valid. We can use numerical weather prediction to load the dice, if you like. There may be one outcome that's more likely than others, and we can look at that information going forward. And this is an example of a product from NOAA where we talk about an 8 to 10 day outlook and a probability of a cold event or a probability of a warm event. So essentially we must be dealing with probabilities going forward and communicating those things appropriately to the users of that information. If you go to the next slide. This is an example of Irene, and this is rainfall, 2-day accumulated rainfall for 2 equally valid forecasts coming into New York State. One was much wetter than the other. As a forecast, each one of these is equally valid. So you can see from these figures, okay, which one do you go with? The impact will be very different in each of those cases. Let's go forward to one more slide, and then what we can do is actually run 75 such forecasts, I think it's 75, where you can get a distribution of rainfall events. And here, actually, I mean, the peak around 125 millimeters in the area we're looking at is still a significant event. But you can see there's a distribution of events. If we go to the next slide, you can see what actually happened. Actually, what happened was we're on the tail of that distribution. And actually, as you go forward in time and use in situ observations, you can tell more or less which part of that distribution you're tending to. But I want to just highlight here the use of probabilistic information is important for making decisions. And something I think that we in the weather community, if you like, are still dealing with how to communicate. And I want to stress here, as we get closer to the event, real-time weather information is crucial importance to know which one of these events is taking place, if you like. Go forward. So high quality, and I'm wrapping up now. So high quality, high frequency weather and hydrological data is critically important for prediction of extreme weather, certainly on the short range, and also for providing situational awareness. So this is important. For numerical weather prediction, you want a good model, but also the model is only as good as the data that's going into it. So you really need high quality data for the models, but you also need high quality data to make decisions about an evolving weather system. So we go to the next slide. I just want to highlight 2 projects that the governor has led in New York State. The New York State Mesonet and the New York State Canal Cooperation flood warning and optimization system. And we've got 2 talks on these coming up, so I'm just going to give you this is just like a commercial for those. So we go to the next slide. This is the Mesonet, which is going to be deploying 125 weather stations across the state to give you this high quality data that you need. And in addition to the 120, included in the 125 sites, which is addressing several gaps, or many gaps in the state, will be some profiling information which gives you atmospheric variables into the troposphere, into the lower atmosphere. So this is important for high-resolution, short-range weather forecasts, but it's also crucially important for situational awareness, and you're going to hear much more about that down the road. Next slide, and I'm going to wrap up. I want to mention also another project, this Canal Cooperation. I mean, flooding is an issue, and in order to understand more about flooding, you need more in-situ measurements about stream flow as well as rainfall, and this is a project that Howard Goebel will be talking about later that we'll be linking with the Mesonet. Next slide, I'm just going to summarize quickly. What has happened in the past? The US has experienced significant trends in temperature and intense rainfall over the past century, and especially in recent decades as And in recent years, we can all remember that very clearly. Projections suggest that that's going to continue, so we may expect even higher frequencies in association with climate change. And of course, we may expect more flooding to be associated with that. And the next slide is what can we do about it? Okay, this is a big issue. We need to curb the emissions of greenhouse gases. That comes back to the big problem. But also, we need to recognize that we're dealing with more frequent extreme weather. We need to be a weather-ready state. We need to be dealing with communications about probabilistic weather forecasts. And also, we need to be doing what we can to enhance and improve the observing network, needed for the NWP, but also needed for this situational awareness. Okay, that's it. And that's it.
Potsdam, can you contact us at maheffle@cisco.com? We just need to get something back from you.
Oh, they did it.
Okay.
You're the host now, Matt? Thank you, Potsdam.
Thanks.
We all set? Okay. Thank you and good morning. I want to talk to you today about some of the extreme weather that can happen in New York and the Northeast and some of the impacts of that. And I want to acknowledge 3 of our students who've helped out with this, and Philippe Papin, Alicia Bentley, and Ben Moore. Okay. Oops, we're not there. We were there.
That's us.
Okay, next slide, please. Can I control the slides at all? Or?
Sure.
I might go a little faster. Yeah, forward the keys, go forward and back, and do it? From those keys, okay. All right, guess I'll let you do it. That's a bit annoying PC, but anyway. Okay, next slide, please. Okay, some predictability challenges that we face in the Northeast. 3 of them I'm going to talk about in particular today. The precipitation location relative to the track of a TC, tropical cyclone. And if you don't get the tropical cyclone track right, that impacts where the precipitation will occur. But the good news is we've been getting better, about 1% a year increase in skill in TC track forecasting. Lake effect snowstorms, which are a bane to the east of Lake Ontario and Lake Erie. Coastal storm location, track, and intensity, and those 3, like we saw a lot of this past winter. And then how do you communicate this uncertainty, which turns out to be something extraordinarily challenging, and I'll have some comments about that. Next slide, please. All right, if you look at TC-related deaths, this is the 40-year study that was done from 1963 to 2012 by Rappaport. And you can see that over 2,000 people perished during that period in the US. These are directly related to TC deaths, almost half of the storm surge. But the second, up in the upper right corner, is heavy rain, inland flooding, like Irene in 2011. And so these are the ones that people are not as much aware of as they are like directly with the storm surge. So that's motivation for one next. Next slide, please. So let's take a look at some notable TC-related inland heavy rain events in the Northeast to just see some of where the rain occurs relative to the track. So just step through these next slides fairly quickly, if you would, please. Okay, Diane from 1955, I was in Northwest Connecticut in the heavy rain. You can see Long Island practically had nothing, Albany had nothing, Boston got nailed, the lower Hudson Valley got nailed. Most of the rain, when it's turning northeastward, is on the left side of the track, which is typical of a storm that's in higher latitudes. But when it came ashore in North Carolina, the heaviest rain was on the east side. So the heavy precipitation shifts from the east side of the track to the west side of the track when the storm loses its tropical characteristics. When that happens, impacts where the rain is relative to the TC track, and that's a critical forecast challenge. Next one, please. Agnes, 1972, Chemung Valley in southwestern New York and the southern tier had monumental floods from 12 to 14 inches of rain in there, most of that precip to the left of the track. Next slide, please. Floyd in 1999 would have produced record flooding around here, except that we had a drought, and then this relieved the drought and then some. Next one, please. Irene, which more of you are going to remember, and you can see how the heavy rain is to the west of the track, and that was in the last week in August in 2011. And then a week later, if we go to Lee, next slide, please. Lee, here's a situation where you can have 2 tropical cyclones in 1 week. By remarkable luck, the heavy rain from Lee did not occur on top of what fell from Irene. But this illustrates part of the prediction problem. When you talk about a 100-year flood, you have a 100-year flood, you're not immune to a 100-year flood for the next 100 years. It may be that the atmosphere is in a very rare, climatologically rare state where the chance of another 1 in a 100-year flood is much higher than the climatological frequency. That's the case that happened here. Connie and Diane in 1955 did that as well. Next slide, please. Sandy, we all know about that. The heavy rain is to the left of the track, but the real issue with Sandy was the storm surge and the wind. Because of the forward speed of the storm, all the high winds are on the right of the track where the storm surge is, but the heavy rain is on the left of the track. So locating where landfall is very critical for separating storm surge and high wind from heavy precipitation. And that's something we really can't do with great accuracy, well, far ahead. Next slide, please. So just summarizing those aspects of what we just said there, and I should also point out that rainfall is strongly modulated by the Appalachians. Next slide, please. All right, so what does the Pacific typhoon have to do with the lake effect snowstorm? Well, this is something that we're getting very curious about from Super Typhoon Nuri last November and looking at as a research item, and it's very interesting, the trail that. So if we start and look at this, next slide, please. There's the track of Nuri from the Japanese Meteorological Agency. It became a super typhoon, which is equivalent of a Category 4 or Category 5 hurricane in the Atlantic. And it moved up east of Japan, and then it kept going into high latitudes. Next slide, please. And you'll have, next slide, please. Have a cyclone that became extratropical, became equivalent to the strongest extratropical cyclone ever observed in the modern record in the North Pacific Ocean. It filled up the whole North Pacific circulation and then totally disrupted the large-scale circulation. If we go to the next slide, in there. So these are some, I'll show you some schematic cartoons of what the flow looked like. Nuri is there in the southwestern Pacific. You get outflow from the tropical cyclone. You see the wavy pattern, the solid contours of the heights of the 200 millibar surface where commercial aircraft fly about 12 kilometers above the ground, and the troughs and ridges in the wavy pattern. And then the polar jet was along that. The colors are where the jet stream core is. The TC will perturb that jet core, and then there will be all kinds of downstream impacts. So we look 11 days later, go next slide, please. That's on the 4th of November. 11th of November, we're starting to build downstream of what was left of Nuri is now up along the Gulf of Alaska and the Bering Sea up there, and there's a big surge out ahead of that trough and warm tropical air up towards Alaska, and that's building a mega block, which looks like a capital Greek letter omega in the atmosphere, and you'll see that even better on the next one. And then go to the next slide, please. There's the mega block in there, and basically that's a big mound of very warm air, and it's centered over Alaska, so we had baked Alaska in there. And then cold surges come down in the northerly flow on the east side. So this brought onset of winter into the CONUS, into the central and eastern United States. And there were 3 surges, and that was the first one. Next slide. At this time, the final surge goes all the way across the Great Lakes. You see the big blocking ridge over Alaska. Cold front cleared the coast of Florida. Temperatures for the first freezes of the year in Florida, and totally changed the weather regime. And the impact of that big cold surge, which was triggered by initially the impact of Super Typhoon Nuri in the Western Pacific, led to, next slide please, Buffalo snowed under. Next slide please. Snowfall. You can see downwind of Lake Erie, where the snow is, there's in inches of 40 to 80 inches of snow in that maximum in that area. Next slide is the water content. water content was 5, 7, 8 inches of liquid water, and when that melts quickly, that's a problem. Next slide. These are some of the impacts. So there were different coping strategies. This household decided that the best shoveling strategy was to let it melt. But that, jokes aside, that illustrates a real problem with people who could be snowed in and need help, shut-ins. That's a big problem for local emergency management and social services. Next slide. Another big issue was heavy snow on roofs. And through here, look at all that snow. The snow on the roof is higher than the people trying to shovel it off. Next slide. Then you have individuals. This guy had quite the load on his mind, and you didn't want to be behind him if he hit a pothole in there. Next slide. Now, here's what are the issues. The sharp edge of the snow band, you go from snow, no snow, to inside that band in literally a few car lengths. When this happens at night and you don't see it, it's a disaster. This is how you get massive pileups on the freeways. You can have 100 cars and trucks all mixed together. All it takes are 1 or 2 people being stupid, driving too fast, and you wind up with a chain reaction. You're often better off closing the roads. The sharp edges of these lake effect bands, one of the things that makes them so dangerous, and it's something that emergency managers need to really be cognizant of, and knowing where they tend to occur, and shutting roads. Now, I think with so many trucks on the roads now, it's better to just shut the roads down. Next one. Next slide, please. Lake Erie, very warm. 54 degrees C water, 12 degrees C water, and that Arctic air comes over that, you get great big lake effect snowstorm. Next slide. In there. This is a surface map. I want to point out something to link to the Maisonette. In eastern Lake Erie, there's one observation there in the middle of the lake on the eastern end, which shows a temperature 28 degrees versus 17, 18 all along the coast south of Buffalo. And you can see the strong convergence in the wind field and 10-degree Fahrenheit temperature difference across that. That's what's driving that lake snowband. So in the hands of an experienced meteorologist, one observation like that can make all the difference in the world. And that's what's going to happen when we have the Maisonette in place, when you have experienced meteorologists being able to take advantage of the extra observations. Next slide, please. All right, NURI-related predictability issues. Next slide. On October 31st, the Climate Prediction Center in Washington issued a forecast for the month of November, probabilistically going for warm over the northern half of the United States. What verified is on the lower half. So you see, NURI totally upset the forecast apple cart on the extended range. One event in the Western Pacific totally wrecked the forecast for over North America. Next slide, please. So the Buffalo snowstorm, we've summarized these things, and we'll go on to the next and last part of the talk. Next slide, please. All right, endless snows in Boston and life on the edge in New York City, a tale of tales in terms of probability density functions and so on. Next slide. All right, so various models. This is the January snowstorm, which caused so much trouble. This is the European Center model, forecast total snowfall. You see from the 25th of January, and their ground zero is Boston area and just south of Boston, and a secondary area in New York City. Next slide. The operational model, that was the ensemble before. The operational model has ground zero in New York City. This is considered like the premier model in the world. So when they had that started getting the attention of people in New York, and that's when the panic started. Next slide. The American model, though, said, the ensemble model run from the same time. Eastern New England was ground zero. Next slide. This is the deterministic operational high-resolution run. Clearly, the maximum is right around Boston, and New York City was going to be on the edge. That entails the tale. Next slide, please. So what happened? So nearly 3 feet of snow inside that white area, and you can see New York City's on a very strong gradient, so 3 feet of snow on the extreme eastern end of Long Island, close to it, 2 to 3 feet. But in the New York City area, there was quite the gradient of snowfall. Next slide. European Center showing forecast probability of precipitation of at least a foot of snow, 2 different time periods, 24 hours apart. Note that New York City is in the gradient region, Boston's in the sweet spot. Next slide. We have these plume diagrams we now have with ensemble prediction sense to show it. These are 20 members of an ensemble on the Sunday illustrated in through here showing 20 different forecasts. The smallest one was, they have a big cluster here around under 5 inches in LaGuardia, and the peak outlier is over 40 inches. But the black solid curve is the mean, about 18 inches. But you can see there's a huge spread. 20% of your members are saying there's going to be less than 10 inches of snow. You cannot go out and say categorically there's going to be a mega snowstorm when you have ensembles showing that spread. Next slide. Islip, further east, mean forecast is 23 inches. So you can see as you go eastward on Long Island, the ensembles are telling us there'd be more likelihood of snow. Next slide. Boston, they were cooked. The smallest total, the blue, is 18 inches, but the mean is up there around 30. So you can see basically slam dunk from the ensembles Boston, but not at New York City. Next slide. This is what caused all the trouble. The forecast that went out from the National Weather Service on the afternoon of 3:30 in the afternoon on Sunday, showing categorical numbers of 24 to 36 inches all the way across New York, west of the Hudson River, in there. The Weather Service system is set up for deterministic type forecasting. So they could not convey the uncertainty that the accompanying text that went with this. But the media saw that and everybody went bonkers. Next slide. What the Weather Service did was very interesting. They put on Facebook, they put the minimum expected snow a few inches, maximum expected snow about 24 inches in an update there, and the most likely snow representing those ensemble plumes. But the reaction was very interesting. This went out on Facebook, and the Weather Service got bombarded with a blizzard of emails saying, you guys have no clue, because it illustrates they don't understand the probabilistic information. Next slide. So, will probabilistic forecasting go viral anytime soon? Next slide. People don't believe that forecast. These are over 2 million forecasts. They're reliable. Forecast frequency on the x-axis, observed frequency on the y-axis. Forecasts are extremely reliable in there for probabilities. So forecasts, this is through 2004. They're even better now. That comes as astounding news to a lot of people who think probability is just throwing dice. They are very reliable. Next slide. Oh. Looks like we may have no more. Forecasts decrease with time. The more convective the storm is, more mesoscale, the skill level goes down, which is why summer thunderstorm forecasting is so much more challenging. Next slide. All right, so why does Dr. Strangelove's deterministic right arm keep going up? There are good reasons. Deciders want cover for unpopular decisions. Cost-loss ratio thinking is not a household term, but if you're going to use probabilistic information, you need to know about cost-loss ratios. Emergency managers make yes-no decisions. Election officials are very risk-averse, and the educational challenge of probabilistic thinking. Next slide. So various cartoons come out in the media mocking forecasts. Washington Post, next slide, through here, the next one. You see things like that groan in there. They make good stories, but you know the Weather Service director is going to have a long day with a headline like that in the Washington Post. Next slide, in there. Next slide, please. All right, last piece. This happens everywhere. Scottish motorway closed for 48 hours due to 6 to 10 inches of snow. Scottish transport minister in denial eventually resigned. Next slide. The European Center forecast, there were 50 ensembles. This is a source from Tim Houston, my colleague and friend at the European Center for Medium Range Forecast. There were 8 different logical scenarios, to reiterate what Chris said, that could have happened. What verified was in blue, 6 to 10 inches of snow, rush hour, widespread disruption. There's only a 10% probability of that, but that's what happened. But each of these scenarios was equally likely. Next slide. So the customer reaction. Thanks, Tim, that's really very helpful to all those things. Then the next customer reaction will be, next slide, so what is the blank forecast? See, people want determinism. Next slide. So the problem, a PDF is a relatively simple concept. We should be able to convey meaningful probabilities to the customer, but the reality is there's an interdependence among these different PDFs, and you have bimodal PDFs and clusterings, like in the plume diagrams we had for LaGuardia. Next slide. So this is the last one. Probabilistic outreach. The transition to probabilistic forecasting will require a hard-nosed assessment of the challenges of operating in a deterministic world. And there are some suggestions for pushing ahead. And the one in red, I really want to make that point. Communicate better and make common cause with social scientists, because we don't do a very good job, not a good enough job in communicating. And tongue planted firmly in cheek, start a weather lottery. All the sports betting that goes on in this country, people says they don't understand probabilities, but they understand odds in sporting contests, how we have to figure to connect those. And then the last point, Tim Hewson made the point, quote, the impact of suddenly admitting that we don't really know what is going to happen tomorrow, having been telling people for years how accurate our forecasts are should not be underestimated. So this is the brave new probabilistic ensemble world that we need to deal with. Thank you.
All right. So good morning. A pleasure to be here again with you. I want to thank Chris for allowing me the opportunity to come out and talk about the wet side of the house. I run the Northeast River Forecast Center. We do river forecast modeling and forecasting for a good chunk of New York State, stretching from the Buffalo Creeks in western New York down the Mohawk, the Hudson, up into the Adirondacks and all points east across the six states of New England. The Susquehanna drainages south of the Finger Lakes region is actually taken care of by our sister River Forecast Center, which is located down at State College, Pennsylvania. I'm going to come at my little 15 minutes of fame strictly from a practitioner's standpoint. What my River Center does is all about understanding the behavior of how water makes its way from Lance's wild atmosphere into your neighborhood rivers and streams. That's what my office is there for. The forecast services that we provide are provided to offices like the Albany Weather Forecast Office, the Brookhaven office, Buffalo, and Binghamton in Burlington, Vermont. So my forecasts go to those weather offices, and they have the delicate task of the boots on the ground, of working with a lot of you independently and individually in the emergency management community to help with your decision-making and the activities that you need to take preemptively, we hope, in advance of oncoming river water. So I'm going to come at this looking at both what is happening atmospherically and how that is affecting the hydrology and the response in the rivers and streams. So on to the next slide. So again, as I said, from a practitioner's standpoint, looking at what we see and what we've been observing the last 50 to 100 years, and trying to make some sense of how is this impacting the behavior of flooding in the state of New York in particular. Next slide, please. Some would call this job security for me. Others may say it's urban renewal, but it is the stark reality of what is happening not only in New York, but across so much of the Northeast United States. I'm humbled by the fact that since I became the hydrologist in charge in 2007, we have had record flooding somewhere in my service area every single year. Thus far, with all this record snow in the east, Mother Nature's been kind to us. We very gracefully have melted the snow, but I know full well, as Lance does, what can happen to us in May and June, so stay tuned, as we say. But we are not alone. You're seeing examples of flooding from our Canadian border region on the St. John River in Maine in the upper left, the Richelieu River Basin, which was devastated by record flooding coming from Lake Champlain flowing into Quebec province. That event was in May of 2011, but it was overshadowed by the devastation of Irene's record flooding in the Schoharie and parts of the southern Hudson Valley, of course, later that August. And then my hometown of West Warwick, Rhode Island, where I kind of had my aha moment, was back in March of 2010. So record flooding abounds all over New York and New England these last at least 20 years. Next slide, please. So the first question that often gets posed to us is, do we have a common theme? Is there some sort of theme with these recent events? And from a hydrometeorological standpoint, there is. Researchers in places such as Florida State and Rutgers, Chicago, over the last several years have been looking at the atmospheric flow regime. And there is a mathematical term called sinuosity, which is a way for us to mathematically measure the curviness or waviness of the atmospheric flow, what carries our storm systems around the hemisphere. And one of the things they are seeing is a clear trend toward a wavier or blockier pattern. Take Lance's example, looking at Typhoon Nori in the Pacific, and how many undulations there were in that upper atmospheric pattern, the number of kinks in that jet stream, the fact that we had this monster blocking omega system over Alaska, baked Alaska as it referred to. We are seeing this with far greater frequency. Okay, so what? What does that mean? Well, what it prompts and produces over New England because of our place on the planet are slower moving weather systems, systems that can sit here for several days and just pound on us continuously. The Mother's Day floods in the Merrimack Valley of Massachusetts, a great example in 2006. Or we can get a blocked up atmosphere where we have multiple systems in a row, Irene and Lee 5 days apart, where we can get hit as we did in southeast New England in 2010 by 4 major massive rainfall producing systems in just 5 weeks, where it's all happening on here. So we kind of get stuck in a rut. Well, what's feeding these systems is this tropical connection. And the image you see here on the lower right is atmospheric water vapor. And there is a tongue of deep moisture in that yellow and red that is coming through the tropical Atlantic, the Gulf of Mexico, and right up into, or up the East Coast. Where New York is placed on the planet is in sort of a dubious position, because our storm systems can get us from the Atlantic side, feeding on that tropical plume. Systems coming across the Midwest can grab onto Gulf Coast moisture, and some can actually tap the tropical plumes. So we have many ways of getting all of these ingredients together. And if you slow down the atmospheric flow, these systems are going to have more of an opportunity to rain or precipitate down on us. And this is how we believe the combination of a warming climate, warming oceans, is making hay with the atmospheric flow, and why we're seeing what we're seeing in this part of the United States. Next slide, please. So just a quick example here with my crude arrows. You can see how wavy that atmospheric flow pattern was back in 2010. If you look at the purple H, that block of high pressure is the big Greenland block, the anchor for so many of our weather systems. When that gets stuck there, the weather systems have one place to go. That are slowed down, tap Gulf moisture, and come right on up the East Coast. A very, very active pattern. And when you get a blocked up atmosphere, it doesn't always mean you're on the bad side of things, but when you're on that eastern edge, that's a bad place to be. And it fosters slower moving or multiple weather systems affecting New England and the state of New York. And we believe that this is tied into the loss of deep ice cover in the Arctic region, because you're changing the differences in temperature globally from pole to equator. And the atmosphere has to make up for that loss of temperature difference. And the response is to increase this waviness and the tendency for a blocked up atmosphere. So that's the hypothesis behind why we believe we're witnessing what we're seeing in changing temperature and precipitation. Next slide. Common themes then, the fallout or the sensible reality of what's going on atmospherically is that the state of New York is experiencing increased annual precipitation. And as Chris mentioned, an increased frequency of these really big high impact rainfall events. We are seeing warming annual temperatures, no doubt. And we are seeing, oddly enough, wild seasonal to season variability in the snowfall. It's sort of become feast or famine. You're either at one extreme or the other. And normal is simply the machination of those two divided. We are seeing a shift in what we call the design storms, that 100-year or 50-year, the 1%, 2% one-day rain events. And we'll talk briefly about that and its impacts on how we've designed the mechanisms and means by which we move things like stormwater around the region. And where we're really seeing the flood impacts right now are on some of these smaller watersheds, generally less than or around 800 square miles or less. And there are reasons for that. So I'm not trying to make a point here that climate change is driving more flooding. I think it is truly a combination of the impacts of temperature and increased precipitation and land use. It really is a very devilish combination, which to some degree is why I think we're seeing the biggest impacts on the smaller watersheds, because arguably they would have the least capacity to deal with even modest changes in rainfall. Next slide, please. So in this graphic, you have on the left annual temperatures for the entire state of New York, and on the right you have annual precipitation. I selected the period 1930 to 2014 solely because of its linkage to when many of the river gauges operated either by State of New York or by the U.S. Geological Survey or Corps of Engineers, our cooperating agencies. When many of these gauges were installed, you'll see a big increase in gauging in the late 1920s, early 30s, and then another big increase in gauging in the 50s after some of the devastating floods throughout New York and New England. So the point I want to make here is really focusing your attention not so much on the trend. The trend is pretty clear that we are warming, but you notice it's not really a straight line. There are all of these undulations. Part of it's natural variability and part of it's luck of the draw of how the atmospheric pattern has set up. But what is clear to me is that it's no accident that our warmest years have all occurred since the 1970s. And that statewide, look at our inability to maintain cold, sustained cold weather, year-long cool temperatures. This has a direct impact on soil moisture, on vegetative state, and on the ground's ability to deal with excess rainfall. It changes the type of precipitation in the late winter or early spring. Where we used to see lots of snow, we're seeing more fall in the form of rain, but before the vegetation has begun to sprout. And that affects the ground's ability to absorb and retain moisture. And then on the right-hand side, look at how many of the years now that we have experienced since 1970 in excess of 50 inches of rain statewide. And our inability in the brown circle on the lower right-hand graphic to have sustained dry years. We're simply not drying the place out like we used to. Next slide. One way to tease out the soil moisture is to look at precipitation deficits, and by using the Palmer Drought Severity Index, you can do this. Again, I'm showing all of these statewide, but for those who want to dig more, if you go to the Climate at a Glance site that I have up there, that CAG is what that stands for. It's known as Climate at a Glance. You're actually able to break down these same analyses I'm showing you here for yourself, by station, by climate region in the state. I've just, for brevity in the sake of time, just showing this to you on a statewide perspective. But looking at the Palmer Drought Index, it is very clear that in the early 1970s, following the big 60s drought, we had a massive flip, and we've continued this propagation of wetter, 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 wetter since the early 70s. What you're seeing here is any of the brown bars are indicative of drought. The more negative the number, the more severe drought. The bars are annual totals. So if you look at multiple groups of bars together, you're looking at multiple years of sustained dry weather, drought. Look at how different the regime is over us today. That directly affects soil moisture. In the fall and in the late winter and spring, we are trending toward a much more primed period for flooding because the soil moisture hasn't had the opportunity to dry out like it used to. So our river flows tend to be a little higher. The soil moisture tends to be a little wetter so that we have less capacity by nature's own graces to help us retain that water and slow down its arrival to the rivers and streams. So with that, let's talk very briefly about what we call the frequency of rainfall. So much of our infrastructure is defined by what we call that design storm. One of them is the 100-year rainfall event, the amount of rainfall that has a 1% chance of falling in a 24-hour period any day of the year. The color graphic behind the lines is indicative of kind of the new state that we're in. And you'll notice that for much of eastern and southeastern New York, from the Mohawk Valley to the coast, the latest study from the Climate Center produced in 2010 was showing that we're seeing now, we should be planning and designing for rainstorms in a 24-hour period that have a 1% chance of happening of between 6.5 and 9 inches. What the contours show you is what the early 1960s study showed and what we've actually designed for, something 2 to 3 inches less in parts of the state. This has big implications to communities and municipalities and how we design, the types of culverts, the amount of clearage we leave beneath bridges, the amount of capacity we need in the stormwater systems to carry this moisture, to carry this water from point A to point B. Just to put a plug in, NOAA is updating formally the old 1961 study to replace the interim climate study. Thanks to the DOTs in the states of New York and New England who put money forth to help get this off the ground. It's seriously a big thank you. NOAA is expected to have this atlas completed either late this year or early next. And then all the communities will be able to access this at various time constraints, durations, intensities in GIS and KXML formats and a variety of formats for you to do what you need to in your communities. Next slide. So I want to end briefly by just looking at how are the frequencies changing. One way that we like to do this at the River Center is to take the points we forecast for, and in this case, again, I have these types of images for all of the basins in New York that we forecast for. I'm showing you the cluster in the Hudson Valley, which includes the Mohawk, Schoharie, and the main stem Hudson. The individual forecast locations are on the bottom, but what's more important is to look at where we were prior to 1970. We have normalized the data, so what we've done is we've taken a gauge and we've looked at the total number of floods at various magnitudes, and we've simply normalized that by the number of years in that period of record. And when you do this, you're able to do a much better job of looking at comparisons and trends. To interpret the data, basically, if you're seeing a frequency somewhere around 0.5, you're probably getting a flood every 2 years, every 3 years. If you're looking at something closer to 1, it's a flood every year or multiple floods in a year. So just for quick interpretation purposes. This is where we were in the decades up to 1970. And you'll notice that for many of the points in the Hudson, you're seeing flood frequencies around, a 0.4 or 0.5. Next slide. Look at how much we've jumped. Everyone is approaching now a flood a year. In reality, what we're seeing is not only an increase in the frequency of flooding, but an increase in the number of years where we're getting multiple floods in a year, or in an and/or increased magnitude of flooding. But it varies by basin, it varies by location. And yes, throughout the state, there are watersheds I forecast for that aren't necessarily seeing such a jump. Some of those are where we have flood control reservoirs, the Genesee, because of Mount Morris Dam. But what I will tell you from my forecast experience, they are manipulating water a whole lot more than they ever used to, because of the increased rainfall and runoff. And lastly, just to tease that temperature piece, prior to 1970, notice that our greatest frequency of floods statewide would occur in the month of March. And if we go one more, you'll notice, next slide, you'll notice that we're seeing more floods now in the months of February and January. So where we used to see, certain times of year having the magnitudes of floods or the peak floods, depending on where you are in the state, we're actually seeing a bit wider or more spread out period of flooding, not necessarily all in March. We tend to see more April floods now, and also floods in December and January. And again, I think that is in response to the way the temperature patterns are evolving and our tendency to have less sustained cold and less frozen ground on the tail ends of the seasons necessarily, and more liquid precipitation during the months of December or even into January now. So with that, last slide. We've become a hotspot here in New York and New England, and it's by no accident, truly, that we're seeing this shift in precipitation and temperatures and a shift in the flood frequency and behavior throughout the state of New York and New England. Thank you.
So this is where we're going to open it up also to our statewide questioners. We have time for about 3 questions. For those who are at remote sites, I'm going to ask that when you come up, first your moderator has got to raise his electronic hand so that we know that you're trying to get on. We'll unmute your campus. We will mute Albany. That way there won't be any problems. If you have a question here in the room, the microphone is about 2 rows in. Please queue on the microphone, and we have about 10 minutes that we're allowing for questions. Are there any questions here from the room? It looks like we have one. Just watch the dashboard.
When the media talks about flooding, the focus is usually on property damage, power outages. Better? As I said, when the media talks about flooding, the focus is mostly on property damage, power outages, and the displacement of people. But from what we've talked about today, it appears to me that a severe flood event could have especially disastrous environmental consequences resulting from the runoff from concentrated animal feeding operations, which are quite extensive in New York. I'm just curious if that's if you agree with that, if that is a significant increasing risk. And if so, do we know if the EPA or DEC is doing anything specifically to take that increasing risk into consideration? Thanks.
It's not my do the same thing. Are we on? Not my area of expertise, honestly. The only experience I've had is really more with algae blooms, Gulf of Maine in particular, where freshwater infiltration into the Gulf of Maine does introduce nutrients that helps the productivity of the bloom. That's been my experience. I know in the Gulf Coast of the United States, certainly hypoxia has been a huge issue due to heavy rainfall and increased runoff and what it's doing to the ecosystem and the ecological environment. So I think your questions were it's not my area of expertise.
Any other questions from the room or any other questions from the other campuses? Anything more?
Don't see any.
Okay. So at the other campuses, they're getting ready to move into their local programming. They are putting on very regionally specific programs, and so they have other panels that they're ready to move to, as do we. And so I'd like to ask for a final round of applause for our presenters from Panel 1. Christopher Thorncroft, Lance Bozard, David Ballard. Gentlemen, thank you. Local campuses, it has been a pleasure, and we thank you for working with us. Were more than a few moving parts on this broadcast, this webcast, but I think we got through it, and I'm very grateful to Cisco for their persistence on this. So at this point, what we're going to do, feel free to break in place. Local campuses, we're going to go ahead and let you sign off. We'll start getting ready for Panel 2. For here in the room, we have actually a very special opportunity. It's going to take us for about 5 minutes, and for that period of time, it's my pleasure to introduce David Russo, the newly appointed Dean of the University at Albany's College of Emergency Preparedness, Homeland Security, and Cybersecurity, with information about the university's newest edition that's certainly appropriate to the content that we're providing here today. David.
Good morning, and thank you for coming here to this wonderful event. I just wanted to take a couple minutes to introduce myself and talk a little bit about the new College of Emergency Preparedness, Homeland Security, and Cybersecurity. As President Jones said in the introduction, the university is delighted to be having been chosen by the governor for this very, very important opportunity to serve New York State and to train the next generation of leaders. The University at Albany is building on an outstanding base in terms of these three areas. If you look across our campus, we have a broad range of disciplines working on atmospheric sciences, cybersecurity, homeland security. We have graduate and undergraduate programs dealing with all these areas. We also have extensive research going on in severe weather, in terms of terrorism, weapons of mass destruction, geography and planning. And we also have extensive training operations. We work through the National Center for Security and Preparedness in Rockefeller College to work with DHSES to put on a great deal of training out at the State Preparedness Training Center. We also have the School of Public Health funded through New York State and the CDC to do a number of different programs for health preparedness. So we have a lot going on at the university. It's interdisciplinary, and what the governor has given us is an opportunity to draw these different disciplines together, to strengthen the existing programs, and to look for opportunities to build in areas where we don't have tremendous strengths at the moment. But rather than go through what we're doing now or what we want to do, what I'd like to use this moment for is an opportunity to say we want to do something different here at the University at Albany. We want to build our academic programs not in isolation from people like you, but in partnership. We want to draw you in and have you talk to us about what sort of academic programs are going to produce students that are going to be able to have successful careers in areas that you currently are active in. We want to work with you to think about training that we're doing on our campuses and facilities throughout the state. And we also want to talk to you about research opportunities. Right now we have a great deal of research going on, but we'd like to have you help us set that agenda. When I look 10 years into the future and think about this new college, I'll measure my success here as our ability to partner with you in a reciprocal relationship, where you're meeting with us on an annual basis saying, these are the sort of problems our organization is facing? Do you have teams of graduate students and undergraduate students that can analyze these problems? Here is a very important research question that has emerged in the last year. How can the University at Albany and its partners throughout New York State help us analyze this? And so today, I think I'd like to invite you to contact me, to work with me over the next year and a half or so, to develop the new college, to begin putting programming out. I think it is a rare opportunity. How often do we have an opportunity to set up an entirely new college and to design curriculum for the next 50 or 100 years? And so I want to thank you for coming today, and I'll be around here for the whole event, and I'd be delighted to talk with you about the new college. Thank you.